Hello friends, in the previous lecture we have seen that what is meant by groups. Also we have seen that semi-groups, monoids. Also we have taken one example on the previous lecture. So today we have to also discuss examples on group. So let us start. First example. The set Q with binary operation multiplication. Set Q means set of rational number with binary operation dot, right? Is not a group. Is not a group. What is your example? Set of rational number with binary operation dot means multiplication is not a group. So this set is not group. Why? Because this set is a not group because all non-zero this set is not group because all non-zero elements in Q means set of rational number has inverse in Q, but if A equal to 0, is a member of rational number, if we take A is 0 is your rational number, then it has no inverse. It has no inverse with respect to operation dot in Q, right? So set of rational number with binary operation dot is not group because all non-zero elements in Q, that is we have to take all non-zero elements in set of rational number has inverse in Q, but if we have to take the element A is equal to 0 in rational number, then it has no inverse with respect to operation dot in Q. That is if A is equal to 0, then A inverse is not belong in Q, right? If A is 0, then A inverse is not belong in Q because if A is 0 with binary operation is multiplication and the inverse of 0, that is multiplication inverse of 0 does not exist in set of rational number. Okay. So let us we have to take the next definition. What is meant by? So next definition we have to study what is meant by abelian group. Okay. So what is meant by abelian group? That is we have to study new point or new definition. What is meant by abelian group? So write down a group G comma dot. A group G comma dot is said to be abelian group is said to be abelian group if a set G with binary operation dot means product or multiplication is said to be abelian group if dot means your binary operation is product or multiplication if your binary operation dot is commutative in that set G. Okay. If your binary operation dot is commutative in your set G, that means that binary operation dot satisfies commutative property. That is if A dot B equal to B dot A. Okay. That is A dot B. What is your commutative property? If A and B, for all A and B are members of that G, right? This is your commutative property. If for all A and B are members of G, then A dot B equal to B dot A. That is your element A and B from set G, and your binary operation dot satisfies the commutative property. Then this group G is said to be abelian group. Okay. That means if your group G is abelian, that means G is also group and it satisfies one more additional property, that is commutative property. then that group G is said to be abelian group. So let's take the examples. Let us take the example. So your first example on abelian group. So that is the Q star with binary operation dot. Next example, R star with binary operation dot and C star with binary operation dot. Right? Now what do you mean by Q star? Q star means set of non-zero rational number. What do you mean by R star? Set of non-zero real numbers. What do you mean by C star? C star means non-zero complex number. With all of these have binary operation dot. Dot means multiplication, right? Or product. Is abelian group. Is abelian group. Okay. So why this is abelian group? Because it is obviously Q star means non-zero rational number with operation dot. It is also true that means it satisfies closure property. If we have to take any two rational number A and B with product of A and B also member of Q star, because both are non-zero, then its product also non-zero. So closure property satisfied. Second property is also satisfied. Third property is existence of identity. So non-zero rational number with operation dot or multiplication. So multiplied identity is 1. Already we have studied in the previous lecture. Multiplied identity is 1 and additive identity is 0. So multiplied identity is 1 and last is existence of inverse. Okay. So if A is element of Q star, then there is element B also member of Q star. That is A and B are these are your non-zero rational number. Then A dot B equal to 1. Right? That is A dot B equal to 1. 1 is your multiplied identity. So what is your B? So therefore B equal to 1 upon A. Right? So A is non-zero rational number. Then 1 upon A is also non-zero rational number. Therefore B belongs in Q star. Therefore B is multiplied inverse of A. Right? So if A is non-zero rational number, then its multiplied inverse is 1 upon A. Right? So multiplied inverse is also exists. And your last property for abelian group, that is satisfies commutative property. Okay? So A and B are both non-zero rational number. Then A dot B, right? A dot B, which is same as B dot A, because your operation is multiplication, right? So A dot B equal to B dot A. That is your multiplication satisfy your commutative property. Therefore Q star and with operation multiplication is abelian group. Similarly R star with operation multiplication also abelian group, and C star with operation multiplication is also abelian group. So let's go and take the next example on the abelian group. Your Q star means set of non-zero rational. Your R star is set of non-zero real number, and C star is set of non-zero complex number. Okay? So let us take the next example. Example 2. Let 2z equal to, let the set 2z equal to collection of all 2x such that x is member of z. Okay? Your set 2z is collection of all 2x, where x is integer. That is your set 2z is collection of all multiple of 2. That means it is set of all even integer, right? 2z is set of all even integer, right? So 2z is set of all even integers, set of all even integers. Okay? Then prove that 2z with binary operation addition. Then prove that the set 2z and set of all your integers with binary operation is addition is abelian group. Is abelian group. Okay? We have to show that or prove that set of even integer with operation addition is abelian group. Okay? So let us we have to prove that set one by one property. So I have solution. your first property is closure property, right? So now first property is closure property, right? What is your closure property? Let A and B belong in 2Z, okay? That we will take two elements A and B from 2Z, when A equal to 2x and B equal to 2y, right? Because A and B are member of 2Z, therefore A is multiple of 2 and B is also multiple of 2. Where A is 2x and B is equal to 2y, right? And x and y is also member of Z, right? Where x and y is member of Z, that is integer, okay? So A and B is member of 2Z. Then your binary operation is addition. We are going to check that A plus B is member of 2Z or not. We have to show that prove that means A plus B is belonging to 2Z. So what is your A? A is 2x. What is your B? That is 2y. Okay. So take 2 common outside. So that 2 times x plus y. Okay. So that is your called as 2x dash. What is your x dash? X dash is x plus y. Now x is integer, y is integer, so addition also integer, called as x dash, and x dash is also member of Z. Okay. So we get a plus b is equal to 2x dash. Right? So we get a plus b equal to 2x dash. That is multiple of 2. That means a plus b belongs in 2Z. Therefore closure property is satisfied. Right? Therefore addition satisfies closure property, right? Therefore addition satisfies closure property, right? Now next property is, so your second property is associative property. Your second property is associative property. Let A, B, C are member of 2Z. Okay, A, B, C are three elements from 2Z. Therefore, where A is 2x, B equal to 2y, and C equal to 2Z. This is your Z is small z. Okay, all this x, y, z, where x, y, z, all these members of your capital Z, right? So capital Z is set of integers. Therefore, all these three elements are your integers, and A, B, C are elements of 2Z. So your associative property is, we have to render A, the binary operation is addition, A plus inside bracket B plus C equal to, so value of A is 2x plus value of B is 2y, value of C is 2Z. Okay. So next step, so 2x. From 2y and 2z, we can take 2 common outside. Inside is y plus z. Okay. So again, we have to take 2 from the both term, take common outside. So 2 into inside bracket x plus y plus z bracket comes in. Again, whole bracket comes in. Okay. Now x plus inside bracket y plus z, and all these x, y, z are member of capital Z, and capital Z is abelian group. That means it satisfies associative property. So using this associative property, we can rewrite them as x plus y bracket comes in plus z. Okay. So from this to how to write down this from this derivative, because x, y, z are all these three members of your set of integer, and set of integer is abelian groups. That means it satisfies associative property. By using this associative property, we can derive this directly as x plus y plus z, and directly write down as x plus y bracket comes in plus y plus z, because x, y, z are members of capital Z, and capital Z with binary operation addition is abelian groups. That means satisfy associative property. Okay. So next step, we can distribute 2 inside bracket 2 into x plus y plus 2 into z. Okay. So next step, distribute 2 inside bracket, then we get 2x plus 2y bracket comes in plus 2z. But value of 2x is a, value of 2y is b, a plus b bracket comes in plus c. Okay. So what is the left hand side? A plus, so we get a plus inside bracket B plus C equal to A plus B plus C. Therefore, binary operation addition satisfies the associative property. Therefore, associative property is 4, right? Therefore, associative property is satisfies. Therefore, associative property is satisfies. Next, third property is existence of identities, right? Third property is existence of identity, right? So your third property is existence of identity. So what is the existence of identity property? Let A equal to 2x, member of 2z, right? And your x is member of integer, and 0 equal to, we can write 0 as 2 into 0, right? We can write 0 as 2 into 0, which is also member of 2z, okay? So 0 is equal to 2 into 0, which is also member of 2z. Then A plus 0 equal to, what is the value of A? A is 2x, value of 0 is 2 into 0, okay? So from 2 take common outside, x plus 0, right? And x plus 0 is again x. So we get 2x is, value of 2x is A. So therefore we get A plus 0 equal to A, right? Therefore 0 is your additive identity. That means there exists identity is 0 in that set 2 0, right? So therefore 0 is additive, 0 is additive identity, 0 is additive identity in 2z, that is set of integer, even integer, right? 0 is additive identity in set of even integer, right? So next, fourth property is existence of inverse. Next, fourth property is existence of inverse, right? So what is the existence of inverse? Let A is equal to 2x, which is member of 2z, right? Then there exists an element B is equal to minus 2x, right? And here x is also member of integer. X is integer, then minus x is also integer. Therefore, there exists an element B equal to minus 2x, right? Which is also member of 2z, because x is integer, right? Now, A is 2x, member of 2z, there exists B equal to minus 2z, also member of 2z, such that A plus B equal, value of A is 2x, value of B is minus 2x. Now 2x minus 2x is 0. 2x minus 2x is 0. So we get A plus B equal to 0. That means your B is, and 0 is your additive identity, and B is your additive inverse, right? Therefore we get A plus B equal to 0. Therefore B is additive inverse. B is additive inverse of your A, right? B is additive inverse of A in 2z, okay? So we get there is inverse in 2z, and the last property is property number 3, that is commutative property. Okay? So what is the last commutative property? Take two elements, let A is equal to 2x, member of 2z, and B equal to 2y, also member of 2z. A and B are member of 2z, and where x and y are integers, okay? And x and y are integers, and we know that set of integer with binary operation addition is also abelian group. Therefore x plus y we can written as y plus x also, okay? Therefore for commutative property A and B are member of 2z, A plus B equal to 2x plus 2y, that means 2 take common, x plus y, and x plus y are integer, and set of integer with binary operation addition is also abelian group. Therefore, x plus y we can written as y plus x. Why we can write this written as y plus x? Because set of integer with operation addition is abelian group, right? Set of integer with operation addition is also abelian group. Okay. So we can write this as next step, distribute 2 inside the bracket, then we get 2y, 2x, that is b plus c. So therefore we get a plus b equal to b plus c. That means it satisfies commutative property, right? Therefore commutative property. Therefore commutative property is satisfies. Commutative property is satisfies. Therefore, all these 5 properties, that is closure property, aspect property, existence of identity, existence of inverse, and commutative property is satisfies. Therefore, set of even integer with binary operation addition is abelian group. Okay, is abelian group. Okay, is proved. Okay. Similarly, we can take 3z is also abelian group, 4z is also abelian group. So by using this example, for in general, nz, where n is a natural number, is also abelian group with binary operation is addition. Okay. So by using this one, we can write our node. So node nz with binary operation addition. Nz with binary operation addition, where n is natural number, is also nz with binary operation addition is also abelian group. Okay, is also abelian group. Okay, so that is 2z, 3z, 4z, 5z, 7z. All these are with binary operation addition are abelian groups. So I hope all parts of today's lecture you have understood. So remaining part we will study in the next lecture. Thank you.